Welcome back to the deep dive. Today we're tackling something absolutely critical for commercial buildings, variable air volume, or VAV systems.
Right. We've gone through a load of technical sources, AHRA standards, research papers.
Now we've basically distilled it down. 4 core design tips plus some key insights on ducting. The goal here is better performance, lower costs, and definitely improved comfort.
Exactly. VAV systems are, they're everywhere. They're the backbone. But seemingly small design choices. They can lead to massive long-term energy waste or comfort nightmares.
So our mission is to get you up to speed on the latest best practices, what the research and standards, especially from HHAR, are telling us now.
Yeah, moving beyond some of the old rules of thumb.
Okay, let's dive in. The sources point to 4 key areas for optimization, and the first one seems like the biggest lever: standardization and controls. Tip number 1, use HHRA guideline 36 sequences. Now that sounds pretty technical. Why is G36 considered like the best of class approach?
Well, think about how it used to be. You'd hire 10 engineers, you get 10 completely different control sequences for VAV systems.
Right, custom coded every time.
Exactly. And prone to bugs, super time-consuming to commission, a real headache to maintain. Guideline 36 aims to fix that.
So standardization is the key word here.
Totally. The idea is simple. Engineers just spec, use AHRE Guideline 36 sequences. That's it.
And the manufacturers handle the rest.
Pretty much. They pre-program these sequences, they test them, debug them. It means lower first costs because you're not paying engineers to reinvent the wheel every single time.
Okay.
And crucially, lower maintenance costs down the line because these sequences are standardized and proven. Commissioning gets way easier too.
Okay, that makes sense from a process standpoint. But what about the actual performance? Can you give us an example of one of these advanced sequences in G36 that makes a real difference day to day?
Sure. A great one is the dual max VAV control logic. This is especially for VAV boxes that have reheat coils.
Dual max. What does that do differently?
So conventional VAV controls can sometimes struggle, especially at low loads. They might hunt or oscillate, trying to maintain temperature. Dual max actively manages both the heating maximum airflow and the cooling maximum airflow set points at the same time.
Ah, okay, so it's coordinating them better.
Precisely. And the research shows this leads to better comfort stability, less fighting between heating and cooling, and, importantly, lower fan and reheat energy use compared to the older ways of doing things.
And G36 isn't just about individual boxes, right? It helps optimize the whole system. I saw a mention of trim and respond logic.
Yes, trim and respond is fantastic. It's about making the central plant smarter. It automatically resets things like the main duct static pressure set point or the supply air temperature.
Based on what the zones are actually asking for.
Exactly. Based on real-time demands, often looking at damper positions or valve positions out in the zones. If the zones are happy, the system can, ease off, maybe raise the supply air temp a bit or lower the duct pressure, saves a lot of energy.
But doesn't that run into the issue of the rogue zone, that one space that's always demanding maximum cooling or pressure?
Yes. The rogue zone. You always have one, it seems. Maybe it's got a huge solar load or maybe a piece of equipment is failing.
And if that one zone drives the whole system,
then you lose all those potential energy savings for the entire building. The central system stays ramped up just for that one problem area.
So how does Guideline 36 handle that?
It uses something called an importance multiplier, or IM. If you identify a zone as being a rogue, constantly demanding extremes, but maybe it's not critical, an operator can set its IM to 0.
So you basically tell the system, ignore this zone's demands when calculating the overall reset.
Exactly. You lock it out from driving the trim and respond logic. It still gets controlled, but it doesn't force the entire plant into high gear. This preserves those system-wide energy savings for everyone else. Really clever.
That is clever.
Yeah.
Okay, let's move to tip number 2. This one tackles VAV box sizing and minimum airflow. The sources claim boxes are often way oversized, like 3 times bigger than needed.
Yeah, that's a common finding. And because they're oversized, the minimum airflow settings often get set way too high, just based on old habits or overly conservative data.
So what should the minimum airflow be set to? What's the modern standard?
The guidance now, especially with HHRE Standard 90.1 2019, is crystal clear. Set the VAV box primary airflow minimum set point equal to the minimum ventilation rate required for the space.
The ventilation minimum, often calculated using standard 62.1.
That's the one. Calculate your minimum ventilation air using 62.1, usually the simplified procedure, and that number is your minimum airflow set point for the box. Nothing higher. unless needed for temperature control, obviously.
But hang on, what about the manufacturers? Their catalogs often say the box can't control accurately below, say, 25% or 30% of its maximum CFM. Doesn't that conflict?
It absolutely does conflict. And this is a huge point, that manufacturer catalog data is often, well, let's just say, overly conservative, sometimes just plain wrong for modern controllers.
Why is it so conservative?
Think about it from their perspective. They need to cover themselves for the cheapest possible controller installed under the worst possible conditions, maybe with bad ductwork right at the inlet. Their published minimum often corresponds to a velocity pressure around 0.03 inches water gauge.
Okay, so what's the reality with good equipment?
The reality is most modern, properly specified BAS VAV controllers are incredibly accurate down to much, much lower velocity pressures. We're talking 0.003 or 0.004 inches.
Wow, that's an order of magnitude lower. 0.03 versus 0.004.
Exactly. It's a massive difference in turn-down capability. So the key for you as a designer or specifier is to demand BAS VAV controllers with a proven minimum velocity pressure capability of 0.004 inches or less.
And then just ignore the higher minimum listed in the general catalog data?
Pretty much. Specify the capability, ensure it's provided, and then you can confidently set your minimums down to the actual ventilation requirement, saving significant fan energy.
Okay, but what if, even with that super low 0.0004-inch capability, the actual calculated minimum ventilation airflow still corresponds to a velocity pressure below what the box can accurately measure? You still have to deliver that ventilation air somehow.
Right, good question. That's where time-averaged ventilation, or TAV, comes into play. AGHRA 62.1 allows for this.
Time averaged, meaning you don't have to deliver the minimum constantly, second by second.
Correct. You can average the delivery over a set period, usually calculated based on a 15-minute window for control, though the standard allows longer averaging times. A G36-compliant controller knows how to do this.
How does it work in practice? Does the damper just cycle?
Essentially, yes. It will pulse the airflow. The controller will drive the damper open to deliver airflow at the lowest controllable rate for a period, then maybe close it completely, then open it again. The goal is that over that 15-minute rolling window, the average airflow delivered meets or exceeds the required minimum ventilation rate.
Got it. So it meets the code requirement for ventilation over time while still allowing the fan to run at the absolute minimum possible level most of the time.
Exactly. Maximum energy savings while ensuring proper ventilation.
Okay, that covers airflow minimums. Let's talk components. Tip number 3, use fan arrays. What exactly are these?
Fan arrays, instead of having one big single fan in the air handling unit, you have multiple smaller direct drive plenum fans arranged in an array, like a grid.
And what's the advantage of having lots of little fans instead of one big one?
Several big advantages, actually. First is redundancy. If you have, say, 10 small fans and one of them fails,
The other 9 can pick up the slack.
usually yes. The remaining fans can often ramp up their speed slightly to maintain the total required airflow until you can get the failed one repaired or replaced. This is especially robust if you use multiple VFDs, variable frequency drives, or the newer ECMs, electronically commutated motors.
So built-in reliability, that's huge. What else?
They often reduce the overall physical length of the air handling unit, which can be really helpful in tight mechanical rooms or retrofit situations.
Space saving, okay.
They also tend to have better acoustic properties, lower sound power levels compared to a single large fan moving the same amount of air. Quieter operation.
Interesting.
And they've enabled the trend towards what some people call mega AHUs, really large air handlers, sometimes over 500,000 CFM. Using arrays makes these huge units feasible, and having fewer, larger AHUs can reduce first costs and save building space overall.
Makes sense. All right, tip number 4, tackle something notoriously tricky. Measuring outdoor air accurately.
Oh yeah, this is a persistent problem. Those outdoor airflow measurement stations, the AFMS devices you see installed in intake ducts, they struggle.
Why are they so inaccurate?
Several reasons. They have trouble reading accurately at very low air speeds, which happens often when you're only bringing in minimum ventilation air. They're very sensitive to turbulence, which you often get near the building intake. Wind blowing across the louvers can mess up the readings too, and they get dirty dust, moisture, even bugs can foul the sensors over time.
So the readings drift or become unreliable.
Exactly. The sources we looked at were pretty blunt, saying that actually controlling minimum outdoor air within the typical 10–15% accuracy required by code is seldom actually possible using these conventional AFMS technologies in the field.
That's kind of shocking given how important that measurement is for IAQ and economizer control. So What's the better way? How can we accurately control minimum outdoor air?
The most robust method recommended is to control minimum outdoor air based on differential pressure, or DP, across a fixed orifice.
A fixed orifice, like what?
It could be the intake louver itself, if it has known characteristics, or a dedicated mesh screen, or even just a section of the duct with a fixed, known open area.
Yeah.
Instead of trying to measure the air velocity directly, you measure the small pressure drop as the air flows through this known restriction.
And that pressure drop is more reliable.
Much more reliable, especially at low flows. This DP method gives you a stronger, more stable signal, typically 2 to 3 times higher than the signal from a velocity probe at low speeds.
Okay.
It measures accurately down to much lower air speeds, around 150 feet per minute. It's far less prone to getting clogged or fouled. And it generally requires much less field calibration, which is often difficult and inaccurate anyway.
So, measure pressure drop across a fixed opening instead of velocity seems more fundamentally sound.
It really is. More reliable, more accurate long-term for minimum outdoor air control.
Okay, great stuff. Let's shift gears now to the ductwork itself, the physical pathways for the air. Our sources dove into life cycle cost analysis for duct design. That's looking at the total cost over time, right? Installation plus energy.
Exactly. LCC considers first cost and operating cost together. And when you do that, some traditional duct design methods like the equal friction method don't really hold up as the optimal approach anymore.
Equal friction. That's where you try to keep the pressure loss per foot of duct constant throughout the whole system.
Right. It's been a standard method for decades. But the LCC analysis points to a different strategy for sizing the main supply ducts. It's called the friction rate reduction method.
Friction rate reduction. How does that work?
The simple way to remember it is start fast and slow.
Start fast and slow, meaning higher velocity near the fan.
Precisely. You start near the air handler with a relatively high friction rate, maybe around 0.3 inches per 100 feet, and consequently a higher air velocity. This makes the ducts smaller near the unit, saving material and installation cost and space.
Okay, so smaller ducts near the start, then what?
Then, as you move downstream, branching off to different areas, you gradually reduce the design friction rate at each transition. So the ducts get progressively larger relative to the airflow they're carrying. You end up with a low friction rate, maybe 0.1 or 0.15 inches per 100 feet, in the final sections serving the VAV boxes.
Why is that better from an LCC perspective? Smaller ducts save up front, but doesn't the higher velocity mean more pressure drop initially?
It does, but the fan is right there, so handling that initial pressure is efficient. Then, by slowing the air down in the longer runs further out, you minimize the total system pressure drop that the fan has to fight against over the building's life. And the lower velocity further out also helps keep noise levels down near the occupied spaces. It optimizes the trade-off between first cost and long-term fan energy costs.
Start fast and slow. Got it. Now, what about sizing the actual VAV boxes themselves, the terminals? So what's the sweet spot there for pressure drop, noise, cost?
The LCC analysis suggests aiming for VAV reheat boxes selected for about a 0.5-inch total pressure drop, or 40 kP, across the box assembly itself. That's a reasonable balance point.
Okay, 0.5-inch ATP, but there was a really interesting specific tip about the reheat coil, something about upsizing it.
Yes, this is a fantastic, easy optimization. The recommendation is to select the box size based on the airflow and noise requirements, like usual, but then specify the factory-installed reheat coil for the next larger box size.
So if you need a size 6 box based on airflow, you order it with the coil from a size 8, while keeping the size 6 damper and sensor.
Exactly. It's often called an oversized coil option. Most manufacturers offer this.
What does upsizing just the coil achieve?
2 really important things. First, putting the same amount of air through a physically larger coil drastically reduces the air pressure drop across that coil.
Yeah.
Less pressure drop means less fan energy used, 247.
Okay, lower pressure drop. What's the second benefit?
The second, and arguably even bigger benefit, relates to the hot water system feeding that coil. Because the coil is larger, it has more surface area. This allows you to design for and achieve a larger temperature difference, or ICAI, on the hot water side. Typically a 10-degree family, larger atrig.
So instead of maybe a 20-degree Fahrenheit drop across the coil, you can get a 30-degree Fahrenheit drop.
Right. And that larger hot water AT is a huge deal for the central plant. It significantly improves the efficiency of condensing boilers, if you have them. And because the water is giving up more heat, you need less flow overall, which allows you to downsize your hot water pumps and piping throughout the building.
Wow, so just selecting a standard factory option for a bigger coil has ripple effects, saving energy and cost on the air side and the water side.
It's a simple spec change with really significant system-wide benefits. Highly recommended.
Okay, last piece. The ducts connecting directly to the VAV boxes. Any key rules from the sources on installation do's and don'ts there?
2 main points stood out. First, avoid using flexible duct directly on the inlet of the VAV box.
No flex duct going into the box. Why not?
It causes problems. Flex duct is rough internally, so it creates a much higher pressure drop than smooth sheet metal. It's also terrible acoustically. It doesn't block noise breakout from the box casing. And perhaps worst, the uneven airflow profile coming out of flex duct right before the box's inlet sensor can actually cause significant errors in the airflow measurement.
So hard pipe like sheet metal right up to the box inlet.
Ideally, yes. Or at least several diameters of straight, hard duct immediately before the inlet to straighten out the airflow for the sensor. Use flex duct only for the final connection, maybe a short piece, from the box outlet to the diffuser.
Got it. Inlet hard duct. Outlet short flex is okay. What was the second point? Something about return air.
Yes, using the sealing plenum as the return air path wherever possible, instead of fully ducting the return air back to the air handler.
So just letting the return air find its way back through the space above the ceiling tiles.
Right. Assuming it's allowed by local code, of course. The savings are substantial. The sources quoted cost savings of around $3 to $5 per square foot of floor area by avoiding all that return duct work.
Wow, that's significant first cost savings.
And it saves operating costs, too. Less restriction on the return side means the fan uses less energy, typically around 20% less compared to a fully ducted return system.
But isn't there a catch? Especially in certain climates.
Absolutely. The big caveat is humidity. In humid climates, you must ensure that sealing plenum is designed and controlled to be slightly positive in pressure relative to the outdoors.
Positive pressure, so air leaks out, not in.
Exactly. If that plenum space becomes negative relative to the outside, you risk sucking in humid, potentially contaminated outdoor air through cracks in the building envelope. That moisture can condense within the ceiling space, leading to mold growth and serious indoor air quality IAQ problems.
So plenum return saves a lot of money and energy, but you need to be careful about pressure control, especially if you're in a humid area.
Definitely. It requires careful design and commissioning to make sure it stays slightly positive.
Okay, this has been incredibly insightful, a real masterclass in modern VAV optimization. We've hit on standardizing controls with Guideline 36, debunking those old minimum airflow myths.
Right, getting those minimums down to the actual ventilation rate, using low VP controllers and TAV if needed.
Introducing fan arrays for reliability in space, using fixed orifice DP for accurate outdoor air.
Yep, ditching those unreliable AFMS sensors for minimum OA.
And then optimizing the ducts with start fast and slow sizing and that oversized coil trick for the VAV boxes.
It really covers the whole system, from the controls logic down to the physical components and installation.
So the big takeaway for you, our listeners, seems to be, don't just rely on the old rules of thumb or what the catalog says the limits are.
Exactly. Doing that is actively costing you money and energy and potentially compromising comfort. You need to embrace these modern, evidence-based practices, specifying G36 controls, demanding low VP controllers, using LCC for duct design. These aren't niche ideas anymore. They're essential for high-performance buildings.
It feels like the path to much more efficient VAV systems isn't necessarily about brand new revolutionary hardware, but more about smarter specifications and control logic.
I think that's absolutely right. A lot of the potential is unlocked by better control sequences and making informed choices about standard components, choosing the right standard components and using them correctly.
So let's leave our listeners with a final thought, something to chew on.
Okay. If these standardized sequences like ASHRE Guideline 36 offer such clear benefits, lower costs, easier commissioning, proven energy savings, and the methods are well documented, why aren't they just the default standard offering from all controls manufacturers on every VAV system? Why isn't this level of plug-and-play efficiency the absolute baseline, the universal norm for every new building going up today? What's still standing in the way?